So I just turned the camera on. I want to pose the problem so that you get the whole picture. Again, you got the car with a magnet in the end of it, a magnet here separated by a block of dominoes. It has the potential energy. You have to do work to get them together. You release it, you get that work back. The closer the magnets are, the greater the potential energy, because the more kinetic energy the car will pick up as the magnets get closer. So we have this potential energy versus separation of magnets. And we can also use U, because this is what you're used to seeing from your mastering physics program, from your text. That's a symbol. It's a traditional symbol. PE is also an acceptable symbol. Didn't used to be, but I started using it, so everybody tried to imitate me. Okay, so we gain kinetic energy here. So what happens? Well, this is an incline at some angle theta, and theta might be 0. It might be a level incline, and you almost hope it will be, because it makes the projectile problem much easier. Okay? So you've got now at least a path for the car to get from here to the edge, and we're going to assume the initial kinetic energy is sufficient to get it to the edge, if theta is 0, which means it's plenty to get it to the edge as long as your slope is downward, because the more downward slope you have, the less kinetic energy you need here to get here. Then thing's going to go off the edge. It's going to land at some point, distance h below, at some distance x from the point below the edge. Okay, and we're going to ignore the fact that the car has a finite length, and when it comes off the edge, it's probably going to tumble some, and you don't know what point of the car is going to hit here, so you don't know how much the body shop is going to charge you. Okay? There. Okay. Well, no, that's probably a painful topic, given that you got rear-ended by a motorcycle this weekend. But hopefully that works out. Okay, so we got all this stuff going on, and we want to break it down. Okay? So let's just say, okay, if we know the potential energy of this thing, what can we then determine? So we want to, I've got the camera going, so I'm not going to wait a long time for this. So think about it. What can we determine if we know the potential energy of this system, this magnet system? Well, that's going to give us some information about how fast the car is going to be going, if we know the mass of the car. Okay? I haven't said that we know the mass of the car. One of my favorite instances of this problem is, you know the potential energy, you know the coefficient of friction, you know how far this is, you know how high it is. So from where it lands, tell me what the mass of the car is. Okay? And that's maybe the way we're going to look at it. If you know everything else, tell me the mass. If you know the theta, you know the A naught, you got the potential energy diagram, and so forth. And you can mix it up. You have all these variables. You have the x, the h, the l, the mu k, the A naught, and the theta, and the mass m. If you know all of them except one of them, you can find that one. So you might think about how the information would be if what you don't know is L, but you know everything else. Okay? Or maybe you don't know the initial potential energy, but you know everything else. How can you find that? Well, what we want to do is we want to relate the set of possible variables, theta, A naught, mu k, m, l, h, and x. By relate, that means find the relationship among all these things. And somebody should have told me to lower the camera. Okay. Camera over there is doing fine. But, okay. So, we want to get an equation or a set of equations or formulas or whatever that allow us to do this. Okay, so that's kind of where we're headed. So we're going to try to develop that whole idea.